Hello, everyone. Welcome to today's Green Tech Media webinar, Flexible System Design Utilizing Cell String Level PV Optimizers. It's brought to you with support from our sponsor, Maxim Integrated. This webinar is part of a series of webinars that GTM does throughout the year to help keep professionals in the solar market informed through research and analysis on the latest market and technology trends. And we're excited about this one today. My name is Scott Moskowitz. I'm an analyst for GTM Research, the market analysis and consulting arm of Green Tech Media. You can stay informed by reading the news on greentechmedia.com and find out more about our research at gtmresearch.com. You can also click the GTM icon at the bottom of your screen for more information about our company. Next slide, please. Before we begin, just a few housekeeping notes. There we go. You'll notice there's a menu bar along the bottom of the screen with several widgets. Some widgets that might be of interest include the Download Slides link, which has a link to download the PDF version of this presentation today, which will have all of the slides you'll see in front of you. The Resource widget on the bottom also has some white papers from both Maxim and Aurora. There is also a widget that allows you to share this webinar through your preferred social media outlet like Twitter, LinkedIn, and others. And on the right side of the menu bar, you can also find speaker bios. We'll try to keep our introductions to the speakers today pretty brief, so please check out the speaker bios to more about those in the webinar. And then most importantly, we want this to be as interactive as possible, so please note that you are able to enter questions at any point throughout the webinar. In the lower left-hand side of your screen. We'll have about 10 to 15 minutes Q&A at the end of the presentation today, which will try to address all of your questions. And with that, let's go ahead and get started on the webinar, on today's webinar. For those that are just joining us, if you're just now entering the platform, the title of this webinar is Flexible System Design Utilizing Cell String Level PV Optimizers. We'll be getting a full overview on this topic from our friends at Maxim Integrated as well as Aurora Solar. I'll pass the baton to them in just a bit, but quickly want to set the stage with some context from what GTM Research is seeing in the market. So today we're going to be talking about residential solar technologies that help to increase the addressable market and make solar accessible to a greater number of consumers. So I want to frame why that's important. First, it's important because residential solar demand is slowing. The market outlook is very good, but the reality is that large third-party installers have struggled financially. Net metering has been hindered in several locations, and much of the low-hanging fruit from a customer's perspective has already been picked. Overall, the ITC extension was a huge boon for the market. In the long-term, market looks great. But the reality is for now, annual growth has begun to slow, and that will be a reality of the next few years. And partially that's because it has to. We've become somewhat accustomed to 50% plus annual growth every year, both in the overall solar market and in the residential market in particular. And now the market will slowly come back to more sustainable long-term growth levels, and we can live with that. And there's still reason to be optimistic. Part of which is that by 2020, solar will be at grid parity in 42 states, with first-year savings from solar of at least 10% in 28 states, which is up from 20 states at parity now, with only 10% offering 10+% savings. And that's why our forecasts show such continued growth in the years ahead. But it's also dependent on a number of factors and trends. The first of which are macro trends that are largely out of our control. So like things like electricity prices, rate battles, public sentiment of solar, topics to pay attention to that matter, but are largely out of the control of most installers. And so moving on, we get more in the wheelhouse of things vendors and installers can control. Falling system cost, inverters and modules continue to fall in price, as do overall installation cost. And we expect this to continue and to further enable growing solar demand. So then lastly, we look at technologies that increase the addressable market. And that's what we'll be discussing today. And then this includes software as well as PV optimizers that enable solar to be economically attractive on typically unsuitable rooftops. Cell level optimizers can make sense in many applications, not just those with partial shading, but it is one of their primary advantages. And so to discuss that more, I'll go ahead and pass it to our friends at Maxim Integrated to move forward with the rest of the webinar. Just real quick though, a quick plug for GTM's upcoming Solar Market Insight Conference. It's our 6th annual one. We'll be discussing topics such as this one and many others. For those viewing the webinar, you can use US SMI 10 for a 10% discount. We'd love if you join us. And now I'll go ahead and pass it to the folks at Maxim Integrated. Guys, go ahead and take it away.
Great, thanks, Scott. We appreciate you and GTM hosting this event for us. My name is Dan Roberts. I'm a senior specialist here at Maxim Integrated. I'm joined today by Sam and David from Aurora. Maxim is a IC company that specializes in fully integrated power regulator ICs for industrial, automotive, and consumer markets. We're founded in 1983, and we had a revenue of about $2.3 billion last year. So our specialty is power electronics and balancing power, converting power. And we've now applied that to the solar industry. Real quick, I'll let David and Sam introduce themselves and Aurora.
Thanks, Daniel. My name is Sam. I am the COO of Aurora Solar. Aurora is a software company that makes sales and engineering design software for the solar industry. Our software is used by many of the top players in the U.S. and overseas. It's used to generate about over 7,000 projects a week.
And I'm David Bromberg, Senior Scientist at Aurora, and I work primarily on developing models and algorithms for getting performance estimates for solar designs, and I'll be talking about designs using Maxim cell string optimizers today and comparing their performance results to traditional modules.
Great, thanks guys. Maxim partnered with Aurora because of their position as a leading modeling services provider, just to validate their model for the performance of our ICs. So what we're talking about here today is our cell string optimizer product. What you see in the background image there is a comparison in size between the optimizer on IC on the right, the little black and silver square, and a traditional PV diode that would go in a junction box. So what we're going to cover is a basic introduction to the technology and its concept of operation, how it operates when there's series mismatch in a string, and how it operates with parallel mismatch in a PV string. And then we're going to go through a few test cases and look at the design benefits under partial shading conditions, under multiple mounting planes, and when you use imbalanced or different length strings in parallel. So we'll go over the first one. Traditional PV modules, as I'm sure most of you are aware, are made up of series connected cells. And then between 20 and 24 cells, whether it's a 60 or 72 cell module, we have a diode wired in parallel. So that your PV string is actually a long string of cells with diodes to cut in every 20 to 24 cells. What happens when you shade a cell in one of those cell strings, whether it's from an object or from soiling or from far shade like a tree, that diode cuts in when the current available from that string drops below the IMP current of the PV string. So this shifts the entire system to a different operating point. And because the diode is an on-off type device, we end up with lower system voltages. We can end up with hot cells because that cell string is in short. And we end up with a local maximum power point in the IV curve that the inverter sees. So to address the problems that occur because of these conditions, we normally design our systems away from these conditions. So we don't design systems with multiple orientations. We don't design systems with shading intentionally, and we don't design with uneven strings. The industry solution for these problems up until now has been module-level power electronics. So adding a DC to DC converter or a microinverter to optimize the output of a module and prevent the knock-on effects from mismatch within the system. So this is module-to-module mismatch correction. You can't totally prevent some of the reliability problems. You have to make a choice between extracting maximum power from the individual module or extracting maximum power or creating hot cells within that cell string. So the module level electronics are making a choice between reliability and power extraction. It does correct the electrical effect of mismatch between modules, but it also includes high commissioning costs and high installation costs because of wiring and additional add-on devices. So the Maxim solution cuts in at a deeper level. We're actually replacing the bypass diode in the 3 bypass diodes in each module with an active MPPT IC, or maximum power point tracking device. So we're extracting the maximum power for the light available, and we're correcting those system-level electrical mismatch effects. All this is done invisibly to the installation crew. So when they pull a module out of a crate, it looks like a standard PV module. There's no additional wiring, there's no additional hardware to add to this module. This is 3 times the granularity of a traditional PV optimizer. So what you get optimization at a much lower level. So when you have a shaded cell string, like in the example to the right, you do extract the maximum power for that cell string, and the rest of the string is unaffected. So if we look at this in the electrical domain, we have a comparison here between standard PV modules and optimized PV modules. So what we're looking at is the power current chart. And what we have here is 2 strings. One of them is shaded and one of them is not. If you look at the black line in the chart on the left, you'll notice that power increases when you draw current up to around 4 amps. And that's where this shaded cell string ceases to be able to provide energy to the system. The blue line in the chart is the rest of the string, which is unshaded. And if you combine those two in series, you get the red line. So you have this local maximum power point or false peak. And then at some point that diode cuts in and the inverter should track up to where that yellow dotted line appears. When you add Maxim ICs to a module, what you get is the PI curve on the right. So you have a large low slope region where both where all the cell strings can contribute power to the entire system. So the shaded cell string is going to contribute power from 4 amps to 12 amps at its own maximum power point. The unshaded string is going to be at the unshaded maximum current, and the two together have a single maximum power point. So essentially your buck converter architecture, which is what these ICs are, allows each cell string to produce maximum power at a range of currents. So the entire system will run at the normal unshaded operating current, and the current from the shaded cell strings will be boosted up at a lower voltage to provide an overall maximum power. If we look at this under parallel mismatch, we get a mismatch in voltage. So for this example, we'd take two strings, a string of 10 modules and a string of 12 modules. If we combine them in parallel in a traditional system, we get the graph on the left. What you see here is three distinct operating points. The shorter string is the blue line. The longer string of 12 modules is on the black line. And the combined system operating point is the red curve. So what you see is three distinct voltages, and neither the longer nor the shorter string can contribute maximum power at the combined voltage. When you add cell string level optimizers, you get a region of voltages at which each string can operate. So again, the blue line is the shorter string, with the blue region being the voltage at which it can contribute maximum power. The black region is the longer string and the region where it can contribute maximum power, and the red region is the two combined. The inverter has a choice of operating points at which it can contribute, or at which it can set the system to extract maximum power. I'm going to turn it over to Sam and David, and they're going to go through a couple practical examples of how this technology works in their modeling software.
Okay, thank you very much, Daniel. As Daniel mentioned, my name is Sam from Aurora, and what I'll be doing at this point is giving you a practical example of how Maxim integrated modules perform. To start off with, what I'll be doing is actually simulating an actual performance. I'll start off with modeling a site. And the way Aurora works is you create a 3D model. From a 3D model, you can extract irradiance, shading, and spatial information. And from that, we'll actually live design a system and then run through a couple of case studies. And at that point, I will ask for David's assistance in explaining the results. So to start off with, I have shared my screen. Hopefully you can see my screen at this point. And we will commence designing a solar installation for a site. And to do so, I move this green icon on the map over to the house for which I will be performing my solar design. Next, I click on 2D. And what I do is I click on the Draw Roof tool. And I will start by placing these nodes at all of the vertices of this particular building. So from the user's perspective, it looks like all you're doing is simply outlining a map image. But from Aurora's perspective, what we're doing is pulling up the geocoordinates of each of the various nodes that you click on. So essentially, we're pulling up the lat-long coordinates of each of these points. And that is a very robust process because what we'll do with that information is we will convert that into a 3D model. And from the 3D model, we can use that to perform our shading analysis, to pull up the spatial characteristics of the site so we can make sure that we have a very accurate remote site assessment. For those of you that are logged in and have access to the white paper, please take a look at it so you can see the validation that's been performed on Aurora's performance simulation engine and also on our shading analysis. So now that I've outlined the roof surface, the next thing I do is I click on this button over here, Detect Roof Structure, and that runs Aurora's proprietary algorithm to automatically identify your azimuths. I'll go ahead and add some obstructions on this site because they will be important for shading purposes. So I see a chimney over there, and on this south-facing roof face, I see that there are some small obstructions, which I'll make sure to identify as well because we wouldn't want to place solar panels in those locations. Finally, I'm going to add some trees. And to start off with, Aurora starts off with an approximation of the height of the tree based off of the diameter of the circle you draw in 2D. We'll convert this into a 3D model and use that to improve the accuracy of our shading analysis. All right. The final step is we want to make sure that this is an actual realistic design. So I will click on this Detect Edge Types button, which automatically identifies the edge types, so ridges, rakes, eaves, etc., and applies the appropriate fire code setback to them. So that took me about a minute. I'll go into the 3D section over here, and you can see Aurora extracts all of that information and builds a 3D model for me. If I click on Lift Roofs, you can see Aurora's initial estimate of the 3D structure of this building. But what I'll be doing is downloading LiDAR data. And for those of you that may be unfamiliar with LiDAR, it's essentially a data set that is generated by a plane, in this case, flying over the location. It has a laser scanner attached to it, and it basically scans the site and measures how long it takes back to receive the pings that it sends out to the site. Based on that information, we can generate this general 3D model that you see in front of you. And now I can use that 3D model to go ahead and change the characteristics of the building. So I'm going to use that to pull up the height of my chimney over here, if I can try and spot it. Sorry, let's zoom out a little bit. So I'm going to use that. It looks like the chimney is approximately 4 feet tall. And I can also use it to adjust things such as the height of my trees and other such objects. If I needed more accuracy, I can also toggle into Street View, and that way I can look at my building in Street View side by side with my LiDAR data. Just to give you a preview as to what we'll be doing, we actually use this information to perform our shading analysis. It's not required, but it's recommended because it means that your site is as accurate as traveling to it for the purposes of shading. And what we do is we simulate the sun's path over this 3D model, and we can see that there's shading caused by trees, by chimneys, and some of the other obstructions that we have on the site. So at this point, I'll go to the process of actually designing systems in Aurora, and that's where we will start off with just looking at a standard module design. And the first step in this process is to run my shading analysis once again. So I gave you a visual demonstration of how we simulate the sun's path for every daylight hour of the year. What this will do is actually give you a heat map so that as you hover your mouse across your roof surface, you can pull up some pretty precise information as to what your solar axis percentages are, your irradiance values, and other information that you may require to perform an accurate site assessment. So as I hover my mouse over this roof surface, you'll notice that in this bottom left corner, there's some shading caused by these trees. And let me go ahead and pull up some additional values, monthly values for you. So you can see exactly how the irradiance changes in this bottom left corner. Over here around the chimney, you can see that there's some shading caused by the chimney itself. And just in general, by examining the color scheme of the site, you can see that, as expected, the south-facing roof surface looks like a good location to place our modules. So I'll start off by selecting standard modules that I wish to place. And in this case, I will go with 2 rows of 12 modules each, select the portrait orientation, and hit Create. So now I have a block of modules, and I will place them in this bottom left corner. And I can already see that this particular module is overlapping a setback, so I'll just go ahead and delete that. And so we have an approximately 6 kW design. That's 23 modules. I'll add an inverter now. So let's choose a 5 kW inverter. And I will connect these 2 strings to this inverter. And you'll see that Aurora automatically assigns the different strings to multiple MPPT ports of the inverter. Let's go ahead and save that particular design, and let's create a new one. And this time I will call them Maxim Integrated Modules. Once again, I want to place a similar array on this particular roof surface, and I'll try and match the location exactly so that we can have an apples-to-apples comparison. And delete this one module once again, and we will select the same inverter so that the only difference between this and the previous design is essentially the type of modules used. So before we move to the simulation section, I will go ahead and recap what we've done so far. I created a 3D model of the location. I used LiDAR to ensure that we have pinpoint accuracy of the site. I simulated the sun's path over it, both visually, and I ran Aurora's proprietary shading analysis engine in order to pull up how much irradiance and shading they are on various points of this roof surface. I created two designs, one featuring standard modules and the other featuring Maxim integrated modules. And you can see that these are pretty much the same design with that one exception. So at this point in time, I will transfer this to David Bromberg so we can go ahead and analyze the simulation results of the standard modules versus the Maxim integrated modules.
All right, thanks a lot, Sam. So before we get into the results of the case study, I first want to give a little bit of background on Aurora's performance simulation engine. So we run a full circuit simulation of a design, meaning for every component, every panel, every inverter, every optimizer, we build a circuit model that physically and mathematically captures the behavior of that component. And then we wire all these equivalent circuits together. So for example, with panels, we wire them in series and in parallel to exactly reflect the stringing configuration in a design. So in this way, we're very accurately able to estimate the performance of a design throughout the year. About a month ago, we released a submodule performance simulation engine. So we actually simulate at the cell string level. So we build an equivalent circuit for every cell string in a design and then wire those up in series and in parallel. So because we simulate at this granularity, we're able to model the effects of bypass diodes inside of a module, but we're also able to model the effects of cell string level optimizers, which is why we're going to be able to accurately assess designs using Maxim technology. Once we wire our equivalent circuit together, we update its parameters given the irradiance and temperature that we calculate with our shading engine, and we simulate the behavior of maximum power point tracking for every daylight hour of the year. So with all this in mind, we're now going to run our first simulation, which is using the standard modules. So we will click Simulate and dispatch our simulation. We see a little bubble in the top right showing us that it's running. And as I said, we're simulating the behavior of maximum power point trackers for every daylight hour of the year. The results have come back. We see a monthly breakdown of production. We also have an annual total. We're looking at about 6.3 megawatt hours or so. Scrolling down, we have a loss diagram showing exactly where our energy is being lost in this design. It's split up into 4 categories: irradiance, which shows us how much light we're losing due to things like shading or soiling. Then there's DC and AC, which shows us where our electrical energy is being lost, and finally miscellaneous losses. And what I'd like to draw your attention to in particular for this design is the about 12% energy we lose to environmental conditions in the DC category, and that's what we call the electrical loss we have due to shading. So because some of our modules are sitting in the shade of that tree, we're losing a lot of energy there. So with all this in mind, now we're going to go to the Maxim design. Again, keeping in mind we had about 6.3 megawatt hours of production for the traditional design. So we're just going to click Simulate again. We're simulating the behavior of MPPTs now, but this time at the cell string level. And so now we'll see how that affects the results, which have just come back. So we're now looking at an annual total of about 6.9 megawatt hours, so roughly a 9 or 10% increase in production. If we scroll down to our loss diagram, we can see that we've mitigated that shade loss by quite a bit. We're only at about 5.5% now, so we cut that more than in half. One other thing I'd like to point out is that there's no mismatch loss in using cell string optimizers, as Daniel pointed out, so we also saved some energy there. So this about wraps up the first case study. Quick summary. We had modules in the shade of a tree we looked at how using the cell string optimizers can mitigate the loss due to that shading. It effectively does so in two ways. The first is that with cell string level optimizers, you effectively isolate each cell string from all the other ones, and so if one is performing badly, it's not going to drag down the performance of anything else, something receiving more light with a greater electrical output. And also with bypass diodes, in traditional modules, at best, when we use them, we just cut out that module, so it contributes no power to the total. Whereas with cell string optimizers, even if a module is in shade or just outputting less energy, it's still producing energy and adding on to our total. So we're still gaining some performance boost there. All right, so now we're going to switch over to our second case study, which looks at some of the design benefits we have in using cell string optimizers. We're going to start by clicking on the 2D view of our site, which we've prepared in advance just in the interest of time. We can see that this roof is a little bit more complicated than our first case study. It's got more roof planes. One thing I'd like to point out is that none of them is particularly large in surface area, so we might end up with groups of panels on multiple roof planes here. If we go to the 3D view, that'll be a little bit clearer. We'll be able to see the size of each of these roof planes. We could see the trees on the south side of the house. There are some chimneys or pipe vents on the south-facing roof plane. Over on the west side of the house, and then a couple of smaller roofs on the east side of the house. So that's our site. This is what we're going to try to design solar for. We're now going to switch over to the designs page, and we have prepared two in advance, one using standard modules and one using Maxim modules. We'll get started with the standard ones first. So we've placed essentially three groups of modules, and if we look at the irradiance map, we can see that we basically just put them in the bright spots, so those areas receiving the most amount of light and not in any of the shade. So on the west side of the house, we basically maxed out as many panels as we could fit on that roof plane, and we strung them together and put them into an inverter. Over on the east side of the house, we have two groups of modules, one facing south and one facing east. And you can see what we did is we actually split them up into two separate strings, pretty short strings, but separate nonetheless, and connected them to separate MPPT ports on that second inverter. Now, we did this because, as Daniel mentioned, if we were to string together these modules that receive different amounts of light, which we can clearly see from the irradiance map, the ones facing south are in a brighter zone there, we would have series mismatch, and we would likely just drag down the performance of the modules that are receiving more light. So we wouldn't really have an optimal design, and that's why it's not generally good design practice to string across multiple roof planes. So we split them up into two strings, connected them to two separate MPPT ports, and so this design has three strings and two inverters. We're going to go to the simulations page now, and we're going to check out some simulation results and use these as a baseline performance to compare to. So we've run this in advance just in the interest of time. We're looking at an annual production of about 7.95, about 8 megawatt hours for the year. Scrolling down at our loss diagram, we can see we lose a considerable amount of energy to environmental conditions, about 6% here. And we also, again, have mismatch loss because these are traditional modules with no optimization. So this is our design. These are its results. Now we'll switch over to the Maxim design. And before we get into the simulation results, I want to talk about the differences in the design itself that we were able to change because of the cell string optimizers. So looking at the layout, one thing you might notice is that we only have one inverter now and two strings. So our modules on the west side of the house, we left those alone. Those are exactly the same. But now our two groups of modules on the right side of the house, we have strung those together. And we're now able to do so because the cell string optimizers effectively isolate each cell string from every other cell string in that string of modules. And so if some are receiving less light, such as the ones facing east here, that's not going to impact the performance of those facing south that are producing more energy. So with these optimizers, we can now deal with this series mismatch and string across multiple roof planes. So now that we only have two strings, we were able to use just a single inverter with two MPPT ports, thereby eliminating an entire inverter from our design. So now we'll go to the simulations page. We'll see how this compares in energy. And again, we've run this in advance just in the interest of time. We can see our production has gone up to about 8.4 megawatt hours. So this is about a 4 or 5% boost in energy. Our environmental conditions loss has gone down again with the cell string optimizers, and we have no mismatch loss. So just a quick recap, we had this design where because we had these small roof planes, we had to split up our groups of modules. With traditional modules, we had no choice but to connect them to separate MPPTs on our inverter. With the cell string optimized modules with Maxim technology, we were able to string across multiple roof planes regardless of differences in irradiance, and we were able to save an inverter from the design, and in doing so, we were even able to boost production by a pretty sizable amount. So that concludes our second case study, and we're now going to jump to our last one, which looks at a few of these effects in conjunction, but also introduces the concept of parallel mismatch. And again, we'll start off by looking at the 2D view of the site. We can see this is a pretty complicated house. A lot of roof planes here, large site. It's likely going to need a lot of panels to offset its consumption. If we go to the 3D view, there are a couple things that I want to quickly point out. One thing in particular is that towards the back of the house, there's a fairly tall chimney, and that chimney casts shade on that roof plane. So if we put any modules back there, it's pretty likely that they're going to experience the effects of that chimney. So running our SunPath tool as we did before, we can see the shade from that chimney really cuts across the whole roof plane, even in the summer months. So that's going to cause some shade loss. And just scrolling around at the rest of the site, we can see some of the roof planes aren't too big, so we might have to string across multiple roof planes again. And we do have some trees. They might cause some shade as well, which is another effect that we will have to deal with. So we're going to switch over to the designs now. And again, we will start with a design that we have prepared in advance using standard modules. And just looking quickly through it, toggling our irradiance map, you can see we basically just tried to put panels on the bright spots. Those are receiving the most amount of light. We do have some panels around that chimney towards the back of the house. That's going to cause some shade and potentially lead to electrical losses. We have another string spanning multiple roof planes facing southeast and facing southwest. They receive a little bit different amount of light, and so we will have some serious mismatch effects there. Those two strings are connected to separate MPPT ports on one inverter. And then we have another group of modules over on the other side of the house facing southwest, and those are connected to a separate inverter as well. And they're in the shade of a tree, at least one or two of them are, so that might be a loss that we'll have to deal with. So that's our design. We'll switch to the simulations page right now, and we will get a baseline performance estimate here. So again, we've run this in advance. We're looking at about 13 megawatt hours of production. So scrolling down, looking at our loss diagram once again, we can see we're losing really a massive amount of energy to environmental conditions loss. So this is the shade from our chimney. This is the shade from our tree. This is even the series mismatch we have on one of those strings. And so this is what we're hoping to mitigate in using the cell string optimizers. Again, we have some mismatch loss as well because these are just standard modules. So going to our Maxim design now, we will start by looking at the differences in the design. And again, something you might notice right off the bat is that, sorry, just bringing up the design. One of the inverters is again gone. So what we were able to do here is actually connect two strings in parallel, despite the fact that they have a different number of modules. So this is the parallel mismatch effect that Daniel was talking about. And so now we have three strings. Two are connected in parallel through a combiner box. And so we're able to use one inverter with two MPPT ports. We go to our electrical line drawing that Aurora automatically generates. We'll see this a bit more clearly. What we can see is that we have a string of 11 modules in parallel with a string of 13 modules connected in parallel through a combiner box. So generally, this is not good design practice with standard modules because those voltages will have to equalize, and in so doing, neither string will operate at maximum power. You'll just have an inefficient design. But with cell string optimizers, you can do this, and it won't impact performance. And so those are connected in parallel, go into one MPPT port of an inverter, and we have our other string of 12, which we left untouched, and that's connected to a separate MPPT port on that inverter. So very similar to our last case study, we're able to eliminate an inverter from the design, but a lot of the other effects that we're dealing with are still present. If we go to the 3D visualization of the panels on the site, we'll still see the shade from that chimney falling right on top of our modules at the back of the house. We'll still see the shadow from the tree on those other panels, and of course we still have series mismatch loss for that other string spanning multiple roof planes. So all of those factors still weigh into the energy performance here. We simplified our design a bit by eliminating an inverter. Now we'll see how we've boosted performance in using the cell string optimizers as well. Going to the simulations page, again, remember we were at 13 megawatt hours before, so now we're looking at about 14.2 megawatt hours. This is a boost of, again, about 9 or 10%. One thing that I should have pointed out on the last design is the yield, so kilowatt hour per kilowatt peak, which is an important metric in making a good design for a site. This is at about 1,500 in the first design. It was actually around 1,400, so we've gone up quite a bit there, making this a really attractive design for the site. If we look at our loss diagram, we'll see that we were able to cut down that environmental conditions loss by quite a bit. We're only at 11% loss now, whereas before we were at 18. We have no mismatch loss once again. So we saved quite a bit of energy here and boosted the yield for this site, all the while eliminating an inverter from the design. So that concludes our final case study. We looked at a few effects in conjunction. We saw how we could use the cell string optimizers to allow connecting two strings in parallel even though they had different lengths, and so that helped simplify the design. And we also saw quite a big performance boost. So going back to the slides, feel free to scroll through them later. We've included some descriptions of the sites and the loss diagram showing the performance. This summarizes the results. So in our first case study, we had a performance boost of about 10% when we designed in shade with that tree towards the south of the house. In our second case study, where we had multiple roof planes and we strung across them, we were able to boost our energy by about 5%. And we were able to do so while eliminating an inverter from the design. And finally, in our last case study, as we just saw, we boosted the energy by about 9%. And again, we were able to cut out an inverter from the design by connecting two strings of different lengths in parallel, which we're able to do with cell string level optimization. So that concludes Aurora's part in this webinar. I'm going to pass this back to Daniel, who's going to wrap up, and then we'll start the Q&A. Thanks a lot.
Great. Thanks, David. So the takeaways that we want to emphasize to those listening are that cell string optimizers can improve the function of your PV system by eliminating not only the electrical effects of mismatch at a cell string level, but at a system level as well. And they're going to produce more energy under partial shading, imbalanced parallel strings, and multiple orientations. So these areas that you've traditionally avoided designing into, you can now place modules in those areas and either increase your system size to hit a specific production target, or make more energy in a rooftop that would normally be disqualifying. The Aurora simulation engine has been validated by both Aurora and Maxim to properly model the effects of our optimizers. You can contact either Maxim Integrated or Aurora with more technical questions about this. Our partners in the distribution channel are Jinko, ET, and Trina Solar, and they're currently shipping modules. And then for distributors, you can go to Bright Street, Civic Solar, Sonepar, or CED, and all of them can help you order modules with this technology integrated. We thank you all very much for attending, and we'd like to turn it back over to Green Tech Media and take your questions.
Great. Thank you, everyone. Thank you, Daniel, David, and Sam, for the presentation. For those on the webinar, we still have about 12 to 13 or 14 minutes left, so feel free to keep asking questions. Ones that we don't address in the webinar, we'll try to get back to you by email. So, Daniel, I'll start with you. It seems like one of the most common questions that was popping up were, how do cell string level optimizers compare to what are now pretty standard module level power optimizers, or any type of module level power electronics? So according to Aurora simulations, it looks like the performance gains are somewhere of around 5 to 10% compared to just a standard system with an inverter. How would they compare to systems with module level power electronics? You know, are they similar? If they are similar, do they beat them on price? I'm curious just how you would compare the technology overall.
Sure. So in energy terms, they can outperform your traditional module level optimizers by between 5 and 10%. And a lot of that reason is the granularity. It has 3 times the granularity, or in other words, optimizing a cell string instead of an entire module. So by removing the bypass diodes and replacing them with an MPPT IC, not only does it improve energy output, but it improves reliability. In the first couple slides, we talked about how the module level optimizer is making a choice between extracting maximum energy and preventing the bypass diodes from going into short and improving reliability.
Great, that makes sense. David and Sam, a common question from watching your presentations and watching the screen share was honestly about the LiDAR data. And the first question is that LiDAR data publicly available, or is this proprietary to Aurora?
Sure, I'll go ahead and take this question. As far as the LiDAR data, we get it from a variety of sources. Some of it is public. We also have the ability to import LiDAR data that's acquired privately. So, say, for example, we have relationships with various partners that can acquire LiDAR on demand. We have LiDAR data for, many places in the U.S. There's a link with a map that I can send around, and for a few locations outside the U.S. as well. One point I would like to make is that LiDAR data is a nice addition. It's not a requirement to generate a 3D model. Included in the white papers in the resources section of this webinar, we showed that using LiDAR data, solar axis values were found to be within about 3% of handheld devices. Without LiDAR data, they were closer to about like 5 or 6%. So it's not quite as accurate, but Aurora still works even without LiDAR data. And you can read the NREL validation report there.
Got it. Yeah, maybe you could expand here. So for those of us that are maybe a bit less software savvy, I'm curious, how would you describe how your technology at Aurora differs maybe from some of the other solar-specific tools that are out there, like either Titan or Helioscope or some of the others? Like, how would you say Aurora differentiates? Is it the LiDAR data? Is it something else? I'm curious how you would describe it for.
We're always focused on our product. Our emphasis is that Aurora is a one-stop solution for the industry. That means that you can start off with an address, just like we did in this webinar, and 10 to 15 minutes later, you have your shading analysis. And one thing I want to point out about our shade reports is that they're actually bankable. That means that you can print out a shade report from Aurora, go to one of the rebate authorities, such as NYSERDA, the world's largest rebate authority, I believe, Massachusetts Clean Energy Center, New Jersey, Rhode Island, Encore, City of Roseville. You can print out a shade report and submit that with your application to get a rebate. So they're bankable. Some private financing providers also accept Aurora's shade reports. So you start off with that. You can generate your shade report. You can do your system analysis, do your system design, generate your one-line diagrams. And that wasn't a part of this webinar, but if you want to perform financial analysis or generate a customer-facing proposal, you can do that in all within the same software application. So we've always been super focused on making each part of the software optimized for the residential or commercial solar installer. So our strength at the end of the day, the reason that we do generate so many projects per week is people come to us as a solution for all of their solar design, engineering, financial analysis, and sales needs.
Mm-hmm. Does Aurora provide, do you guys go so far as to do any type of cost-benefit analysis for the technologies that you're installing with, or is providing the performance expectations and bill of materials all that installers really need to do their own form of analysis?
I think that there are various methods by which people perform analysis. For some people, it's cost-benefit. For other people, it's simplicity of installation. For some people, it's performance, aesthetics. What we do is you can perform an LCOE analysis, for example. You can perform a payback analysis. You can generate all of the financial metrics that you would expect as part of a solar installation and even beyond. We have a number of different things you can analyze: net present value, internal rate of return, and not just for modules, but for your design as a whole.
Great, thank you. Okay, Daniel, I'll shoot it back your way to discuss Maxim just a bit. A few questions have rolled in about firefighter safety, things like rapid shutdown. I'm curious I'll kind of expand the question and ask, what are other benefits that can occur at the module level that Maxim offers, is rapid shutdown something that is offered or is on your radar? I'm curious what your impression or what your perspective is on monitoring, especially at a level as granular as the cell string level, or is that the inverter's job? I'm curious if what are the other benefits that occur at the module level from your perspective?
Sure. As far as NEC 2017 and future requirements, it's absolutely on our radar. We've worked with SunSpec extensively, and eventually we'll announce some new products that will absolutely take care of those needs for our customers. So that is definitely on our radar, and we will announce future products that meet those standards. The other benefits that the technology can give, some other loss factors we didn't talk a lot about were partial soiling, where you have modules mounted in landscape and the weather continuously deposits dust and washes it down to the bottom row of cells. That's one application that has huge benefit in array utility scale and larger scale landscape installations. And another source of loss that we didn't talk a lot about was degradation. So uneven cell degradation over the lifetime of the system. And we just chose to focus on some more design-oriented loss factors today, but absolutely those other sources of mismatch are corrected by the cell string optimizers.
Yeah, I'm curious too. You know, monitoring is something that differentiates Maxim from some of the other module level power electronics vendors out there. And I'm curious if that's because you feel that getting the performance gains off of mismatch and other types of losses are the most important thing, or is there value in monitoring at the module level? Is that,
So it all depends on the complexity to integrate. Our PowerPoint tracking and energy management is not dependent on monitoring like some other solutions are. Each cell string optimizer operates independently, so there's no requirement for it. We don't feel that the payback for cell string level monitoring is high enough to justify it as a core part of the system. The industry standards that are already established generally require array level monitoring or monitoring at the point of interconnection. That's where you get your actual revenue grade monitoring. So until we receive a lot of pressure from the market to provide telemetry at the module level or at the cell string level, it's not something that we're focusing on right now.
Got it. Makes sense. All right, just one more question, David, for you. We have about 2 minutes left, so I'll just give you the chance to kind of close this out before we say goodbye to everyone. But you talked a bit about your performance simulation engine. I'm curious if you can tell us just a bit more about that and how it's able to simulate Maxim correctly.
Sure. So as I said, initially we build a circuit model for every cell string in the design. So we build an equivalent circuit model that's been developed and validated by a number of researchers over the years. And then we essentially, for cell string level optimization in particular, we treat each cell string itself almost like its own panel connected to its own maximum power point tracker. And we have an algorithm that we use that is able to really efficiently find the maximum power point for that circuit. The parameters of that circuit are adjusted given the irradiance and temperature on the cell string, which we calculate using our shading engine. So the same algorithms that we use to generate our shading reports, which NREL and now various financing authorities have all decided are very accurate. That same shading engine is used to compute irradiance and temperature on our modules themselves, which we then use a pretty standard model for to adjust these circuit parameters. So we have a model that really physically captures each cell string individually in a design, which is different from other tools which really simulate like an entire array at an aggregate level. So because we simulate at this granularity and we could do maximum power point tracking at that granularity, that's really why we're able to model Maxim. It goes a little bit deeper than that. We also have worked with Maxim very closely to model some of the more non-ideal behavior if it does occur. But really, it's the granularity at which we model, coupled with an advanced circuit simulation and shading engine that enables us to do this type of simulation.
Well, thank you for that. And with that, we'll go ahead and end the webinar. Just a quick thank you to the audience for attending. Thank you to Maxim Integrated for sponsoring this webinar on cell string level optimization. And thanks for Aurora for joining as well. Don't forget, audience members, that we'll be archiving this on the events section of greentechmedia.com, and you can register for more free webinars there as well. So for everyone, thank you. Have a great rest of the day, and we appreciate you joining us.